Hello there. This is video number 3 of section 3.3. So this is actually the last lecture that you will need to be caught up for before your midterm. However, do keep in mind, so this will be, I'm recording this the week before, but so following the schedule, today is Tuesday. Do keep in mind that you do have a midterm later this week, covering up through section 3.3. However, on Wednesday and Thursday, the schedule does have section 4.1 and 4.2. So Friday we have off so that you can work on the midterm. But remember, Wednesday and Thursday, we will be sort of starting the next chapter. All right, so today we're going to look at some interesting geometric applications of determinants. Again, one of these cool things in math which I think makes sense when I look at especially motivating examples like this, but one of those things that I would have never thought of myself had I been I would have never thought to think that sort of the relationship that we're going to look at today would happen. So one of the reasons math is so cool. So anyways, I've got the following rectangle, although the way I've drawn it, it looks a little more like a square, but same thing. Well, not same thing, but so I've got the following rectangle in R2, and I've defined it by I've fixed it at the origin. Two of its points are at the coordinates A0 and 0D, and then of course we've got this fourth coordinate, which is this plus this, so that's the point AD. We can see that its area is equal to A times D because one side is length A, one side is length D. So remember back in section, I want to say it was 1.9, we showed that, of course, well, maybe even before that, we showed that all of these shapes in R2 can actually be thought of as sort of being defined by vectors, right? So remember we showed that each of these points can be thought of as a vector of length 2, and that this parallelogram is actually defined by these 2 points, A0 and 0D, and then this point here is just the sum V1 plus V2. And so, this parallelogram fixed at the origin is actually defined entirely by these 2 points, and then the sum of these 2 points is this third vertex of the parallelogram formed when I fix it at the origin. So that aside, notice so here's sort of the really cool application. Notice if I define A by these 2 points, right? So sort of these 2 vectors that are, in a sense, defining this parallelogram, then well, here's what A looks like. It's a diagonal matrix, A, 0, 0, D. And look at the determinant of A is equal to A times D, which is equal to the area. Notice here I've actually got the absolute value of the determinant of A, which is important because, as we'll see, in fact, the determinant of this matrix is always equal to the area of the parallelogram defined by its 2 columns. But notice that occasionally this determinant can be negative because this shape might be shifting sort of around in the plane. And so we always have to sort of put that absolute value constraint on. And this makes it that I'll never get a negative area. But so it turns out the determinant of this matrix actually gives the area of the parallelogram defined by those 2 vertices. And so we'll see an example of this where we can actually get a little more complex than just a shape fixed at the origin, but we'll state this as a theorem now. So if A is a 2 by 2 matrix, then the area of the parallelogram determined by the columns of A is just the absolute value of the determinant of A. So determinants can also give us, as you can see here, information about sort of the geometry behind our linear algebra. So I want to look at one example that is a little more involved than this one. I certainly think that example on the board is a great sort of motivating example to get an idea why. But we can actually do a lot more with this, because if you think about sort of any shape in the plane, we can always translate that shape to be defined by two vectors that sort of are fixed at the origin. And so we can actually use determinants to find the area of really any parallelogram in R2 if we have the sort of coordinates that it's defined by. So as an example of this, we can find the area of the parallelogram determined by the following four vertices: -2, 0, 0, 3, 1, 3, and -1, 0. So to do this, we want to find an identical parallelogram that is fixed at the origin. So I'm going to attempt to draw a picture of what we're about to do here. So right now we've got, -2, 0 is right here, 0, 3 is right here, 1, 3 is there, and -1, 0 is there. So our parallelogram looks something like this. What we're going to do is we're going to shift it over by a couple units so that one of the points can be fixed at the origin. And then what you'll see is that this vector v1 and this vector v2 define this parallelogram much in the same way that the previous vectors did. And so I can make these the columns of my matrix and then calculate its determinant. And of course, this will be v1 plus v2. So what I'm going to do is I'm going to take this point 2, 0, make that my new origin, and add 2 to all the points. So instead, we're going to use the points 0, 0. So I've taken -2, 0, shifted it over. 2, 3, 3, 3, and 1, 0. And so notice I've just added 2 to the x-coordinate. And now, if I let this be v1, this be v2, then you can see this vector is v1 plus v2. And so the area is going to be the absolute value of the determinant of this matrix. Again, v1, v2. I've shifted everything over so that I can make these the columns of my matrix. And so the determinant of A is equal to 2 times 0 minus 3 times 1, which is equal to -3. But remember, the area is equal to the absolute value of that. So the area of this is equal to 3. So we can use determinants to calculate the area of two-dimensional shapes. It turns out we can actually construct a identical theorem for three-dimensional shapes and finding the volume. So I'm once again going to attempt to draw a picture. In retrospect, actually, this one didn't turn out too bad. We'll see how my three-dimensional drawing skills are. So once again, we're sort of going to use a small motivating example for this. So let's let this be the point A, 0, 0. This can be the point 0. I forget which coordinates I used. A, B, and C. 0, B, 0. And this can be the point 0, 0, C. And if you notice, these 3 points define a cube-like object or a parallelepiped in R3. So we'll call this shape S. And so notice that the volume of S well, it's just equal to the length of its sort of 3 defining sides multiplied together. So that's just A times B times C. But notice, again, if I look at the matrix, if I let A be the matrix defined by these 3 vectors, then the determinant of A is equal to A times B times C. And so much like we did in R2, we get a very similar result in R3. And so all I have to do to change this theorem is change 2 by 2 to 3 by 3, change a few words around, and we actually get the exact same result. So if A is a 3 by 3 matrix, then the volume of the parallelepiped determined by the columns of A is just the absolute value of the determinant of A. So not only do we get a nice sort of, I guess in this case, volume result, so just like in R2 we get this nice result, we get sort of the same result in R3. So that means we can answer a question like the following, where again, we can actually determine the volume of any parallelepiped fixed at the origin. Found a parallelepiped determined by the columns of A, or determined by the points (1, 0, -3, 1, 2, 4, and 5, 1, 0, and we'll say fixed at the origin. And so this problem is a little easier than the last one because we're already assuming this is fixed at the origin. And so if you imagine, it might not look quite as nice as if all of my vectors were on axes, but it's still sort of a shape that's fixed at the origin. And so we can still apply the same idea. So all we have to do is just let each of these points define a vector, which is a column of A. And then we just need to calculate the determinant of A. And so I think in my calculations, I expanded across the third row. So this would be -1 to the 1 plus 3, which is 4, times -3 times the determinant of 1, 5, 2, 1, which is just this submatrix, plus -1 to the 5th times +4 times the determinant of 1, 0, 5, 1. And of course, I don't need the third term because I have a 0 here. So expanding this out, I get -3 times 1 minus 10 minus 4 times, well, 1 minus 0 is just 1. So this comes out to 27 minus 4, which is equal to 23. And notice, since this number is positive, I don't have to change it. And so this would be the volume of the parallelepiped. We can do one more interesting thing with this determinant idea. And I think this is sort of the coolest application that we will see. So in order to see this, remember that every matrix A, and this definitely was something we looked mostly at in 1.9, defines a linear transformation. So if A is an n by n matrix, it defines a linear transformation from Rn to Rn. So if you'll remember, we spent a little bit of chapter 9 looking at some specific types of linear transformations in R2. And so I don't necessarily want to go into specific detail on those transformations, but just remember, if I had some shape here in Rn, or R2, I guess we know this as R2, and I had some matrix A which defined a linear transformation. Well, remember, this shape would get mapped to, maybe some other shape. So that looks sort of like a rotation in a way. But remember that, this would map this two-dimensional object to some other two-dimensional object in the range. And so a natural question to ask is, let's say I know the volume, let's call this object S. And what we'll do is we'll say, let T be the linear transformation defined by T of x equals A times x. So this is just the linear transformation corresponding to this matrix A. And so the question is, if we know the volume, or I guess in this case, the area can we find the area of T of S? So we know how to find the area of S now, right? This is just the determinant of the corresponding matrix to S. But can we find the area of its image under this linear transformation? And the answer is yes. And this is, I think, just such a cool application. So if T is an transformation from R2 to R2, so it would be a linear transformation. Defined by a 2 by 2 matrix A. And of course, they all are, but we'll sort of specify the matrix, 2 by 2 matrix A. So if S is a parallelogram, I have to remember how to spell this word, parallelogram in R2, then the area of T of S, and so note that this is just some number, and so this is the area of the image of S, is equal to the determinant, well, the absolute value of the determinant of A, where here A is this matrix defining the linear transformation, times the area of S. So not only do determinants help us find the area of a shape, they also help us find the area of the image of a shape under some linear transformation defined by a matrix A, specifically using the determinant of that matrix. So looking at this theorem, I want to do one more example, and then we will wrap up. So let S be the parallelogram in R2, defined by the two vectors, -2, 3, and -2, 5. Let A equal the following matrix. And what we want to do is find the area of the image of S under the mapping, where I map each vector to A times that vector. All right, so all we have to do is use this theorem, and we'll be able to do it. Specifically, we have to find the determinant of A, and then we have to find the area of S. But this is just calculating two determinants. So the absolute value of the determinant of A, well, the determinant of this matrix is equal to 6 times 2 minus -3 times -3. So the determinant of A is equal to 3. Next, we want the determinant of this matrix, whose columns are defined by these two vectors. This is equal to -10 plus 6, which is equal to -4. But that means that the area of S is equal to +4. So by our theorem, the area of T of S is equal to 4 times 3, which is equal to 12. So by using two determinants, we can calculate the area of the image. So one more thing. This also holds for linear transformations in R3. So we sort of have a second part to this theorem, where I can just replace all of the 2's by 3's, all of the parallelograms by parallelepipeds, assuming I can spell the word parallelepiped. And everywhere it says area, we put volume. And it turns out that this works the exact same way in R3. So that wraps up this section. We can use determinants to find volumes. So like I said, tomorrow we'll be starting in chapter 4.